Hey everyone. So we're going to continue the review here and pick it up after the polymerization. So we're going into experiment 7. Today we're going to talk about the Fischer esterification reaction or synthesis of isopentyl acetate, also known as banana oil. And so you can review through here primarily different forms of fragrances that are found and their chemical formula. So we create these in labs in order to flavor certain sorts of foods, beverages, and apply things for perfumes to mimic these sorts of flavors and odors. And that's why we're going to be having this odor from isopentyl acetate as the odor of banana oil, because that is the chemical structure. And so what we need to understand here is that if you combine acetic acid and isopentyl alcohol together with sulfuric acid, either as we had placed it into the lab bench for a week, or you can reflux it for about an hour. So one thing to remember here is they have the arrows pointed this way because it is a reversible reaction. It can go back, and so it is crucial for us to perform these acylation and then move forward into having our product, removing that and distilling it so that way we can isolate it. And then we won't have to worry about it going back in that fashion. And so what I'm going to do is show you the mechanism on another page, and then we're going to go ahead and understand exactly what we need to know going into the final for this section. So what happens here is that the carboxylic acid, the oxygen can take proton here in order to create a protonated acid. What happens is that this increases the nucleophilicity of this attacking group. So what happens is then an alcohol can go ahead and attack that carbonyl because it is more available to be attacked, as the electrons can move from the double bond up to the oxygen in order to create a more stable hydroxide species, which is known as a tetrahedral intermediate, where you have a binding of an alcohol on one end and a binding of the alcohol on another. So what happens is, in order to create a hydrolysis reaction, the proton can actually shift over from this alcohol to the acid in order to create a side group that's a water. And as we know, water is stable as a leaving group. And so what happens is part of the reaction called the dehydration step, where the electrons actually go back down to recreate our pi bond or double bond and give off water into the reaction vessel. And so then we're left here with our acylated product. And then finally, deprotonation occurs. And so what happens is that that extra proton that was sitting on there, it can go back into the water in that case. And then you'll be left here with your esterification. So the primary thing to know is from the start, like we had just discussed, is the carboxylic acid, the oxygen must take a proton in order to become attacked at the carbonyl position. So it takes the proton, gets attacked at the carbonyl position by an alcohol to create a tetrahedral intermediate. We have a proton shift to get rid of water in a dehydration step. And then finally, we're left with our ester here. So going forward, make sure to understand that there are two methods to performing this reaction like we discussed. You can put it in the bench or you can reflux it. For the sake of time, we put it in the bench and then we used it the week after. And so that concept of sulfuric acid as a catalyst, we use this acid to provide us some hydrogens to facilitate that mechanism. And so going forward, you can slightly review all of these parts of how we performed the separation and that we went forward in order to do a distillation. That way we could isolate it and leave all of our crud behind. And since this isopentyl acetate can boil at a pretty low boiling point, then that's why we can distill it over, collect it, and then subsequently find out our yield. And so it's good to understand the concepts here. Even though we didn't perform GC, it is good to understand how we would be able to see purity from it. And then the bond peaks of isopentyl acetate. So let's think for a second. If we were to take an IR of isopentyl acetate versus just looking at isopentyl alcohol, what's the biggest difference? The biggest difference here is this alcohol peak. And on here, there's no alcohol peak. So you would not see that large 3000 inverse centimeter broad peak on the IR if you had pure isopentyl acetate. What you would see on isopentyl acetate is a carbonyl group, because the difference here is that there's a carbonyl on the isopentyl acetate, but there is not a carbonyl on the isopentyl alcohol. So that's the take-home lesson today, is that when you perform the esterification, you get a carbonyl and then you lose the hydroxide group. So for instance, if you potentially ran an IR on your crude product and maybe you had a little bit of isopentyl alcohol left over, you might end up seeing an alcohol peak and then also a carbonyl peak because you'd have two mixtures together. But in this case, we went forward and did a good distillation to isolate that isopentyl acetate. You should see no hydroxide peak. You should only see a carbonyl group and then some subsequent fingerprint region for your carbons there. But the primary thing we're going to look for is an ester, like a carbon bound to an oxygen, and also that really high indicator of 1700 for that carbonyl peak. Then going back down, we can also look to see, so the proton and carbon NMR, we can go ahead and look at that and then see the difference. So primarily, you would be having a hydroxide peak over near above 10 for an NMR of isopentyl alcohol. And just like in the IR where we lose that, we would not see that in isopentyl acetate. The only thing we would see in isopentyl acetate would be the protons here on this CH3 group on the left. To be a CH2, there would be one proton and then also the two CH3 groups. So make sure to review through your NMR for this. We gave you the NMR and I gave you feedback on it, so that way that you can see it in action. They should be very similar in terms of isopentyl alcohols with the carbons those don't get changed. The only thing that gets changed is the loss of the proton here from this alcohol group. So you wouldn't see that above 10. And then you would see a sort of carbonyl carbon with the hydrogens there. And then relative to the carbon NMR, you want to think about how there is a carbonyl peak. So that one would be shifted above a little bit above 100 for that carbonyl. And then the other carbons would be very similar to the isopentyl alcohol as well as similar to acetic acid. Across the board, they're going to look very similar, but just make sure to understand how to recognize a carbon NMR and how to recognize a proton NMR and to count them all out. So you have, the 3 hydrogens here, you have 2 hydrogens next to your ester, and then you have 1 hydrogen that's hiding right in between there, and then the 2 CH3s, those will be very close or overlapping on your NMR spectra. And then finally, let's look back down here. And then that was about it for this one. Make sure to go forward and review all of your post-lab questions that we had presented there in that system in order for you to understand. The primary thing I think to take away from this reaction is to understand the mechanism, understand the loss of a hydroxide group in your spectra, such as the IR and NMR, and then just make sure to really understand how the sulfuric acid assists in catalyzing this reaction to go forward for this nucleophilic reaction. So I'm going to go ahead and pause here, and then I'm going to go and switch over to the next part. Okay, so here we're going to go ahead and screen share for this synthesis of dibenzyl acetone by aldol condensation. So the primary thing here is to understand how this aldol condensation works and why we need to use a certain ratio to create our product. So what we're making here is not benzyl acetone, it's dibenzyl acetone. So in this case, the first thing to notice is we have a 2-to-1 ratio of the benzaldehyde to our acetone. And so the main concept we're going to learn today in this experiment is the mechanism of an aldol condensation and how to appropriately apply it so that way that you get the product that you want. So we're going to go forward and observe, here's the reaction, how you put it all together, and primarily having the 2-to-1 ratio of benzaldehyde to acetone. You slowly add it together, and then it's going to precipitate out. And you can review through how the reaction happens itself. But the thing I want to take here today is to kind of walk through a couple of these post-lab questions and then go forward to talk to you more about the mechanism, because I think that the mechanism is the main thing to be taken here. So question 2 here is talking about that. So we'll go over that. And number 1, always practice your actual yield, theoretical yield. You know how to do that. Take the molecular weight, then do your mole ratio, calculate it across, and then you will find your product. And then understanding, review all of your post-lab answers. I've given you the corrections on your papers. If you have any questions, please feel free to email me and contact me, and we can talk about it in further. And then we're going to go ahead and look today at the mechanism so that way that you can understand how that goes on. So we're going to switch over to here. And so firstly, this here is acetone. And what happens is, since we're using sodium hydroxide, there's going to be presence of hydroxide ion, and that itself is going to take away the alpha hydrogen. What happens whenever they take away alpha hydrogen is that the electrons go back to the carbon. So now you can see the carbon is negatively charged. And then what that does is it makes it into a nucleophile. So that alpha carbon can act as a nucleophile, subsequently attack the carbonyl carbon, and then those electrons will move from the pi bond that connects between the carbon and oxygen and go up to the oxygen to create an electronegative oxygen in this case. And so similar to the previous reaction where we had an attack at the carbonyl, it's a very traditional thing in chemistry for attacks to happen at the carbonyl carbon. In this case, the acetone's alpha carbon is the nucleophile attacking that carbonyl. And so then we create this intermediate here where we have our acetone has been attached to that side chain there, and then but we're still left with a negative oxygen. So what happens is, since this reaction is in water, that negative oxygen is going to go ahead and abstract one of the protons in order to become stable. So then it becomes protonated and creates the hydroxide group on here, the alcohol. And so since this alcohol is sitting here, this is a part where a lot of people forgot to do the last step of the condensation. So remember, the condensation, think about like water on your glass. That means that water is going to be given off. And so what happens is that a hydroxide ion, because we're in a basic solution, will abstract one of the protons of the alpha carbon in order to go ahead and move these electrons over and create a double bond. So remember, once the hydroxide has been formed, then it needs to condensate or leave. And so this abstracts the proton, then the electrons move, create the new double bond, and then the hydroxide leaves into the solution as a condensation. Then you're left here, and you're happy because you have your double bond there, but that's not the end of it, because you have a 2-to-1 ratio. You have one more alpha carbon now that can be deprotonated once more. So on the other side of the acetone, now this proton is taken away, abstracted by the hydroxide, because you're still basic, still strongly basic reaction. The deprotonation happens and the exact same thing happens again. So the main thing to understand within aldol condensations is when you do a 2-to-1 ratio with a ketone, the ketone can attack twice. That's why we keep the ketone at a 1, and then you have the aldehyde at a 2. And so this alpha carbon here does the same attack to the carbonyl carbon, that the electrons move up from the pi bond up into the oxygen in order to now have this anion left here. It abstracts another proton and then finally goes through the same steps of condensing or eliminating in order to leave us our dibenzyl acetone product. So just make sure that you understand the primary thing is that you're going to have one ketone and one aldehyde, okay? The ketone can attack an aldehyde and then binds onto it. Now you have one condensation performed, one aldol condensation, because it's aldol, meaning the aldehyde and alcohol. That's the relevance to why they kind of short-term that happens once, and then if it's in a 2-to-1 ratio, then it'll happen again. So the tricky question was asking what happens if you don't use enough, right? If you use maybe one of the acetone and one benzaldehyde, in that case, you would end up having a lot of this. There may be a chance, within the entropy of the system to create a double product, but the majority will be stuck in this situation here where it's just monofunctionalized. So just primarily remember, because a lot of you got the concept of how to do the aldol condensation, but then you forgot to take away abstract the proton and eliminate it in order to create that double bond, and the hydroxide group leaves. So there was a couple people who had, 2 hydroxides on there at that, beta position. And then it was like, okay, good. Now you've done the aldol, but you need to condense. It needs to condense. You remove your hydroxides, and then now you have those 2 double bonds there. And so just to go back really quick to make sure to see if there were any other parts here. So yeah, in the case of adding 2-fold excess of acetone, it would limit it. You would only have so much aldehyde in the system to be able to react. So you would get a monofunctionalized system. Instead of the dibenzyl acetone, you just have the 1. And so make sure to also review the products of acetone and acetaldehyde. I drew them for y'all, but effectively it'll attack and it'll have either one arm coming off, two arms coming off, and then you'll have one arm on both sides and then two arms on both sides. So remember to review through the rest of these. Understand the reaction itself is not very complicated in terms of how you mix things together, you heat it up, and then you're going to go forward and then you're going to isolate the crystals through recrystallization, which is a pretty common action that we do in chemistry. So yeah, just make sure to review through that mechanism, and then I'm going to switch over to the next part. One last thing I wanted to touch on before moving on to the next section is to understand if you were to run an IR or NMR on your samples, what would happen? So looking here, remember, if we're going to have a benzaldehyde, that means we have an aldehyde group here. If we have a ketone, then we're just going to have our carbonyl with the two carbons on each side. In the case of an IR, if you ran it and you were looking at your benzaldehyde or your ketone versus dibenzyl acetone, there will be no aldehyde group found, but you will still have a ketone. So remember that a ketone has a little bit of a different shift in IR relative to an aldehyde group. So you would notice that, and it would change in that sense. Now, if you were in an NMR, on the NMR, you would have an aldehyde proton present in your starting material, but in your product, there will be no aldehyde proton. The difference there that is actually going to be really big if you run an NMR is going to be two things. One is the proton NMR. You'll have a double bond. You'll have protons coming off here, which will be significantly different than either your benzaldehyde or your ketone, your acetone in that case. So in the product, you would see protons that are, near in the double bond region, in the alkene region, you will see those protons present. And in the case of the starting material, there are no double bonds other than just the carbonyl bonds, but those are not showing other than your aldehyde proton. So just make sure if you're looking at an NMR and then you're talking about dibenzyl acetone, that you find one proton there, one proton here, and then one proton on each part, alpha and beta, to your ketone group. Now, the other part of what I was wanting to tell you about the NMR is if you ran a carbon NMR in this case, then there would be significant differences, especially with those double bonds, because you have 1, 2, 3, 4 groups there. So you're going to have 4 peaks that would be relative to that. And they're probably going to overlap because it is a symmetrical substance. So since it's symmetrical, you probably only have 2 peaks, and you'd have one at the alpha position where that double bond is and one at the beta position. That's the big significant difference. And also, you would not have an aldehyde carbonyl peak that you would see in a benzaldehyde. There would not be that there. However, there would be a carbon ketone peak in your carbon NMR. So that would be kind of similar to your original acetone in terms of that carbonyl ketone peak, probably about the same since it's not very much different in that case, but you would not exhibit any sort of aldehyde peak regarding a carbon. So those are the main things to review when you're going to look at analyzing these materials in terms of IR and NMR. Just make sure to know the differences between ketone, aldehyde. They're very close to each other, very close in the 1700 region, but they are different. So the aldehyde, the ketone, those in IR, and then in NMR, remember the double bonds, the ketone, the aldehyde. Remember the functional groups, they'll be your saving grace. Across the board, the protons, you're going to see a similar situation in terms of the aromatics, and the carbon, it's going to be same across the board regarding benzaldehyde relative to dibenzyl acetone. So I just wanted to touch on that very briefly, so that way that you know to kind of take a look at those and understand the differences in IR and NMR. And now I'm going to go and move forward into the next section. Okay, so now we're going to come back here. We're going to look at experiment number 9, which is the synthesis and analysis of aspirin. So the big take home here is that salicylic acid has a phenolic group. So when we're utilizing UV-Vis, the only way that we can actually see an absorbance relative to salicylic acid versus aspirin is because of that phenolic group. So remember that the hydroxy group coming off this benzene ring indicates it's a phenolic group. If we look at acetyl salicylic acid or aspirin, there is no phenolic group because it's an acylation reaction, and that's not going to be present. So when we do our UV-Vis analysis, we're going to be seeing how much salicylic acid is present or the amount of phenolic group present in your substance. And so looking at this here, what we're going to do is come over here and look at the mechanism. And so if we look here, what happens is that you have this anhydride here that what goes ahead and takes a proton from an acid. And so this is similar to the mechanism that we had just previously looked at, where there's going to be a proton on the oxygen, so that way that the carbonyl becomes more electrophilic and it can be attacked in a nucleophilic fashion. So as you look here, the phenolic hydroxy group here, that oxygen can actually go ahead and attack the carbonyl carbon in a nucleophilic addition. Then you get a tetrahedral intermediate. And of course, there's still that proton left there and it's partially positive. So then it's going to go ahead and abstract that proton off of there to make it completely neutral, because we need it neutral across the board for us to get to our end product. So what happens is then over here, a oxygen is going to go ahead and abstract another proton in order to create a different tetrahedral intermediate. And what's happening here is this is occurring so that way we can produce acetic acid as a byproduct. And so now that we have this partial positive here, then it's easy for this oxygen on the right-hand side to go ahead and shift its electrons down, creating a new pi bond or double bond or carbonyl, and then kicking off that acetic acid, because acetic acid is a stable leaving group. It is just in the solution. It's also known as vinegar. So you're going to see it here. The acetic acid is left, and then this proton can get abstracted from the relative anions that are left in there. And then finally, you're left here with your aspirin. So we go from the salicylic acid to an aspirin. So this is an acylation reaction. Remember that once this anhydride is protonated, then the phenolic oxygen can attack the carbonyl. It undergoes a rearrangement, the protons are moved, and then a proton is gained on that side chain. You can see that the acetic acid is going to be produced. Then it is kicked off, and subsequently we are left with our acylated product, which is acetylsalicylic acid. So looking back over here, you can look forward to mainly remember to study that mechanism of the UV-Vis portion, where you're going to have to calculate out how much salicylic acid is left. That's going to tell you how much is there. So if you get an amount that's relative to 10 milligrams and you have 100 milligrams of product, then that means that you have about 10% impurity or 90% pure aspirin. And that's just a rough calculation. Make sure to work through the calculation of that. And so if you go down here, this is the reaction mechanism of how everything happens within the reaction, but we don't need to necessarily memorize every single step. The primary thing is to remember and memorize your mechanism, and then make sure to understand the difference. And if you were to do an IR, then you would see a big hydroxyl peak. So we'll go back up here at the top. If you did an IR of this, you would see a hydroxyl peak for that salicylic acid. And then in the product, that would actually be replaced by having a ketone there. And there's probably a carboxylic acid hydroxyl peak, so they might be quite similar, but it won't be as broad as that big hydroxyl peak would be relative to a phenol. Then if you ran an NMR of this, the difference would be that you would not see this hydroxyl group. You would still see a carboxylic acid because it's in both the starting material and the product. But the main thing is that you would end up having this carbonyl here, and you'd have some protons relative to that, whereas you wouldn't have that on your starting material. So those are the main things you would notice as differences if you were to take NMR, IR. And so primarily here, just make sure that you understand how to go through stoichiometrically, because you are diluting the system here in order to calculate it. So you have to go backwards in the calculations. So please review. Whenever I wrote on the board, you have the picture of how to go backward, how to back calculate and find that. Otherwise here, the only other things are just talking about relative melting point and such, but the main things to memorize for this section is going to be, how do I calculate my purity of aspirin? Of course, theoretical yield, percent yield, how much salicylic acid is left in my product, and how much aspirin is in my product. And then understanding down here how you calculate it out by looking at a concentration curve. So that's the majority of this one. It's pretty straightforward. Now I'm going to take a little pause here, and then we're going to move on to the next section. Here is the last experiment that we have performed for the OChem 2 lab, and it is the synthesis of methyl orange, also known as azobenzene. And the huge takeaway from this is the creation of the azo bond from the diazonium reaction. And what is required for a diazonium reaction is an electrophilic substituent like this NN-dimethyl and a sulfonilic acid. So it requires a starting material that has an amine group on it because we're going to be creating this diazotized sulfonilic acid. And so firstly, what I'm going to do is show you the mechanism, and then we can go forward to discuss further what you should study for your finals. So firstly, we have the sulfonilic acid here, so the SO3H here, and then the amine group. And the important part or take home from this azobenzene reaction or diazonium reaction is the creation of the diazonium intermediate. So what happens is we use a soft base in order to go ahead and make this sulfonilic acid soluble in water solution. And so what happens is then we use sodium nitrite and hydrochloric acid in order to create this diazonium chloride. So it's a diazonium intermediate where this amine group turns into a nitrogen that's triple bonded to another nitrogen. And you can see it here in this step 2, it's created. And that's why we want to make sure it's really cold during the reaction because it can volatilize and decompose. So we want to stabilize that diazonium in order to go forward to do the diazonium reaction. So once we have our diazonium here from the use of sodium nitrite and hydrochloric acid, then we go ahead and we take our electrophilic NN-dimethyl which is the one right here. And what happens is that there's actually electrons on this nitrogen. It's not shown, but it can go down to create a double bond to your ring. And then what happens is the rings, pi bonds will then go ahead and relocate kind of like in the Diels-Alder mechanism. And these will move over one step. The other one, so this is actually the double bond itself attacking that nitrogen. So in this case, this nitrogen is quite electrophilic, so it's going to act as a nucleophile and attack. So this double bond is actually attacking the nitrogen, and then one of these bonds in this triple bond move down over to the nitrogen because nitrogen likes to have 4 bonds, so it's going to stabilize it. And so finally, you're left here with your azobenzene or methyl orange. But the thing is, we still have this lone proton here, and we haven't created back our full benzene rings. So what happens is this proton is given off, and it actually folds back over to recreate this full benzene ring. And then subsequently, the electrons are given back to the nitrogen. So this is drawn incorrectly. There should be a double bond here to this nitrogen, but you know, that's going to move from that pi bond back over to the nitrogen, and then everything is stabilized across the board in terms of where all of your electrons need to be. So like I was saying, the main take home is use an aromatic amine. So there's your amine right there on an aromatic with the presence of sodium nitrite and acid to create a diazonium chloride or diazonium intermediate, then followed by the pi bond attacking the nitrogen to create this azo or methyl orange. And so coming back over to our experiment here, this is the shorthand version of this. And so the thing within this concept that's different than our aspirin lab is that when we're measuring this, we are measuring the product. So azobenzene is photoreactive and it is testable, and around 460 nanometers was where most people had their pi to pi star peak, which is the peak that is shown for absorbance in azobenzene. And so what you're going to do is utilize UV-Vis spectroscopy. And I think at the bottom here, we have the absorbance versus concentration here for methyl orange. And so what we're doing is when we measure that and you get an absorbance value, that tells you how much azobenzene is present. Whereas in the aspirin lab, we were looking at how much salicylic acid is left over. And so relative to that, we will know by utilizing this relative to an absorbance. You can utilize Beers-Lambert law to go ahead and go back and find your concentration, and that'll give you a relative amount relative to the total amount of azobenzene that you have. And through that, you will find your purity. And so that's what is right here, the step 2 of the data analysis, determine your product purity. And that's because, let's just say you put 100 milligrams of azobenzene into a given vessel and you were going to measure it and use spectroscopy. So you go over and you measure it with spectroscopy, and then you found out, okay, so I actually have only 95 milligrams of that 100 are pure. because relative to concentration and absorbance found through that. And so with that result, you know that since you have 95 milligrams of pure azobenzene and 100 milligrams of azobenzene total, that you have 95% purity. So that just make sure that you have that distinction for when you take your final, that in the azobenzene or methyl orange situation, we're talking about the amount of concentration relative to purity of a total sample. Whereas when we're looking at the aspirin sample, what we're doing is when we look at that absorbance, you're finding the absorbance of salicylic acid, and then you would take that and subtract that from the total to find out the total percentage of pure aspirin that you have. So that's the difference between the two, and that's the key indicator here, is teaching you all how to utilize UV vis spectroscopy to find purity, but in two different ways. Whereas in the methyl orange situation, we're finding it of only methyl orange. In the aspirin situation, we are figuring out how much salicylic acid or starting materials left over in order to figure out the final purity of it. So, primarily this was just a lab that is mainly focused on doing the actions of creating the azobenzene. So, we used a lot of time in lab doing that, and then we quickly measured the UV vis at the end to determine purity. Just make sure that you understand the mechanism and that distinction that we just discussed regarding the aspirin lab and the UV vis indicator versus using UV vis on methyl orange or azobenzene. So just primarily review through all the rest of your mechanisms for every lab. Look at those key indicators of what you wanted to study for that specific experiment, and understand why we did things in the way that we did them and what chemicals are required to perform each individual reaction. So thank you for your time, and I'm going to go ahead and end it here.